Welcome to 14.6, where we're going to start by introducing the gradient. And the gradient is actually one of the most important tools we'll have in all of multivariable for the remainder of the year. And the gradient is defined this way. For some scalar function, f of x, y, we're going to define the gradient as a vector function. The gradient of f, so sometimes it's written using this upside down triangle, which is called a del or a nabla. So sometimes we'll say del f or grad f or the gradient of f. But the gradient of f is defined this way. It's a vector function rather than a scalar function whose I hat component is equal to the x derivative and whose j hat component is equal to the y derivative. So it's the x derivative I hat plus the y derivative j hat. And so as just a simple example, right, if we take our classic hyperbolic paraboloid, right, our function x squared minus y squared, the gradient in general of this function, the gradient of this function in general is 2x negative 2y. And if we wanted to calculate it specifically at some point, let's say we wanted the gradient at the point 1 comma 3. Oops, that should be a parentheses. At the point 1 comma 3, we just plug it in. And so the gradient vector at that point would be 2 comma negative 6. In case it's bothering you that we only have two variables, we can define the gradient for more. So if, for instance, we have a function of 3 variables, as we will sometimes, at this point it's just fx, fy, fz. It's really important for me to note that this is a vector function. It takes in a scalar function f and gives you a vector back. It is not fx plus fy. It is the two components of the vector. The gradient has an enormous number of uses, and so we're going to discuss some of them today. And the first one that I want to discuss is what's called the directional derivative. So, if we're at some point on a function, right, here are our level curves of, of f. So maybe here's, f equals 1, f equals 2, whatever, f equals 3. A variety of level curves. We've already talked about, okay, well, if I'm at a given point, here I'm at this point, x0, y0. Well, if I walk in the x direction, right, I can figure out what my fx is. And if I walk in the positive y direction, I can figure out what my fy is. But what if I walk in a totally random direction, right? What if I'm on this map, this contour map, and I want to move in some other direction, right? I don't want to go purely in x, purely in y. I want to walk somewhere. Well, obviously, there is a rate of change in that direction. If I walk in this direction, I'm going uphill at some rate. In this case, I'm going uphill. I could be going downhill. I could be doing something else. And so the question is, can we figure out what a derivative in an arbitrary direction is? And we can. And this is what's called the directional derivative. So the directional derivative of the function f. Now, we do need to do this at a point, at the point x0, y0. So the directional derivative at some point in the direction u hat equals ab. So we need three things. We need a function, a point, and a direction. And I just want to be really, 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 really clear here that this direction needs to be a unit vector. This direction needs to be a unit vector. In any case, if we want to find the directional derivative of f in the direction u, we write it this way. We write du times f, or not times f, du of f, excuse me. And that's going to be equal to the gradient of f at the point we're interested in. And we're going to take a dot product with that unit vector. Because remember, grad f is, of course, a vector. And so this is the directional derivative. So this is one of our more important tools for for calculus for finding these directional derivatives. So let's do a quick example of how to do one of these. So we're going to take a function x squared y cubed minus 4y, and we're going to come to the point 2 comma negative 1, and we're going to take our directional derivative in the direction 3/5, 4/5. And I'm just giving you conveniently here a nice unit vector, and you can verify for yourself that u hat here is a unit vector. So the first thing we got to do is we've got to find the gradient of f. So that's going to mean taking the x derivative, so that'll be 2xy cubed I hat plus the y derivative, 3x squared y squared minus 4 j hat. Now in this case, there's the gradient of f. We do want to evaluate this at the point 2 comma negative 1. So if we plug in x equals 2, y equals negative 1, we get negative 4 comma 8. So negative 4 comma 8 is our gradient vector. So that means the directional derivative of our function at that point is going to be equal to the dot product of our gradient with our direction, 3/5 comma 4/5. So that'll be, let's see, negative 12 over 5 plus 32 over 5. 32 minus 12 is, of course, 20 over 5, which gives us 4. So what that means is that for this function, at the point 2 comma negative 1, in the direction 3/5, 4/5, so we're walking up kind of north-northeast here, that means that we are going uphill, that our rate of change is positive in that direction. Our function is increasing in that direction at a rate of 4. And it's the directional derivative that's actually going to lead us into a better understanding of some of the other properties of our gradient. Because a couple of things that are important to note about the directional derivative, right? What if u equals I? That is, what if we're moving only in the x direction? Well, hopefully it's clear that if we're only moving in the x direction, think about what this dot product is going to be. It's only going to give us the x component of our gradient. That is, it's only going to give us fx. So if we're moving in this direction, then we just get our x derivative. And similarly, if we're moving in the j hat direction, we get purely our y derivative. And for other directions, we get a mix of our x and y derivatives. Another question. How can we make our directional derivative as big as possible? So imagine that you're walking along some function, you're on some hill, and it's leg day. You want to get as strong as possible. Can't skip leg day. So you do want to go uphill. You want to go find the steepest route up this function that you can, up this mountain that you can. So you're looking to maximize the directional derivative. Well, think about this dot product, right? Think about this dot product. When is a dot product maximum? And a dot product is maximum when the two vectors are parallel. When is the directional derivative maximum? When our direction is parallel to the gradient vector. And this actually gives us one of our first really important properties of the gradient, which is that the gradient of f points in the direction of fastest increase. The direction of our gradient vector is, in fact, the quickest way uphill, the steepest way uphill. So if you move in the direction of your gradient vector, that's actually your greatest rate of change. And it's worth remembering that that also means that the maximum value of that directional derivative is actually just going to be the magnitude of the gradient, if you think about how the dot product is going to work. So for instance, for our sample function here, negative 4 comma 8, at that point is actually the direction of greatest rate of change. So that means that, yeah, we're moving in this 3/5, 4/5 direction, but the direction of greatest rate of change is actually negative 4 comma 8 is actually, you know, that is actually up this way. If we walked northwest, we would actually be going even steeper uphill. The second question that I have about this is, what if I want my directional derivative to be equal to 0? Well, remember, it is a dot product. And how do I get my dot product to be equal to 0? Well, this is when my direction is perpendicular to our function. And this actually is our second really important property of the gradient, which is that the gradient vector is perpendicular to the level curves of the function. And I'm not going to lie, this might seem like a big jump, but let's take a little visual example here, right? Let's say we're here at this point. Right? If I move along my level curve, right? If I move back and forth this way along my level curve, as long as I'm sticking to the level curve, my rate of change is 0, right? Kind of by definition, as long as I'm on the level curve, the value of my function is constant. And the fact that this is a dot product actually means that how do I, where is my gradient, where is my direction of maximum rate of change? It's got to be perpendicular to that. So you'll actually find that the gradient vector, wherever you go on a function, is always pointing uphill and perfectly perpendicular to the level curves. It always points perfectly perpendicular to the level curve. And that's actually a tremendously useful property of the gradient. And one of the reasons it's a tremendously useful property is that it allows us to find normal vectors to level curves and surfaces really easily. So one example here down at the bottom that we're just going to do is, let's say I want the tangent plane to this ellipsoid. X squared over 4 plus y squared plus z squared over 9 equals 3. And I want the tangent plane at the point negative 2, comma 1, comma negative 3. Well, what I can do is I can actually grab this whole function of x, y, and z and say, well, if this is my function, x squared over 4 plus y squared plus z squared over 9, what I'm actually looking for is, excuse me, third time's the charm. What I'm actually looking for is the gradient of f at that point. So here it is. We get x over 2, comma 2y, comma 2z over 9. Or given the point that we've got, we get negative 1, comma 2, comma negative 2/3. And it turns out that that gradient vector is exactly the normal vector to our plane. If here's our ellipsoid, right? Here's our ellipsoid. And let's say we're down here at this point, right? This is a level surface where our function equals 3. And as a result, the gradient vector that we just found here is actually going to point perfectly tangent to, not tangent, perfectly normal to our surface. So one of the great uses of gradient vectors is not just in directly calculating derivatives, but in also finding these normal vectors to a wide variety of curves and surfaces. And we're going to play around with that a lot more in class.